Okay, girls, if you remember, we talked about this one, isotope. So isotope, they are elements. Okay, they are elements with same proton number, but different neutron number. Okay, always remember this. Always remember this. So, for example, if you guys remember the question we did, we had barium. I think has 56, yeah. And it says to us that another barium has 139, but it says to us that this barium here is an isotope of this guy. So therefore, since this one is an isotope, we know that this number here will be 56 because it tells us this guy is an isotope. So all isotope, even though they will have a different number on the top, because of this, they will have the same bottom number. Always remember this. Always remember this. And then you can solve any decay equation. Well done. Where are we? Almost done, girls. Almost done. Okay, half-life, medicine, fission and fusion. Let's take a look at our half-life, number 6. Okay, I'm just going to stop there and say something. Girls, I'm taking the time, okay, to go over this with for you. Okay, do have a look at it. Okay, have a look at the video because I'm going through it. Okay, don't just look at the paper on its own. Okay, it may not make any sense. Let's go through the video so that you may understand. Hopefully, it will help you for your test next week. Okay, just want you to know that it is a Friday night. Everyone's gone in the school. I'm just here for you. Okay, so many of you have missed. So some of you may have missed a few lessons. Okay, and I did upload things online. And some of your friends who are here, they do have the notes, okay? But you need to be proactive and ask questions, okay? If there's something that doesn't make sense, you can either ask me, you can either use YouTube, you can either ask your friend, okay? Don't sit in the class looking at the ceiling or looking at the rulers, okay? So this is just for your own benefit, girls, okay? All right, let's carry on. Half-life. You did the practical on this using dice. Let's take a look. What is half-life? Now, radioactivity, it is very, very random. So it happens. So these 3 particles that are giving out, these 3 particles, so we have an atom, and then it just happened that it is unstable, they want to be stable. You give off these 3 radiation. Now, this process is very rare. Oh, sorry, it's not very rare, it's very random. And it is unpredicted. We can't predict it. However, if you have a large amount of these particles of the nucleus, then we can predict it. So what it means that if we have 1 or 2 or 3 or 10, we can't predict it. But if we have more, then we can predict it. That's why when you did the practical, you use many dice, and when you did it, you put your curve, and you find out that all the curve, so even though your practical that you were doing is, so no one except you interfere with your practical. And however, all of you got the same graph. So therefore, with a large number of, in this case, I'm using, you guys use, I think 30 dice, and there were 30 of you in the class. So we're increasing our chances, so therefore we can detect it, we can predict it. Okay, but alone, it is near impossible. Now let's take a look, half-life. What is half-life, and how can we use it? Okay. Right, so half-life, okay. Right, so this one, it is the average time. Okay. Average time it takes for the number of nuclei of the isotope of the particles, not the particles of the atom. Okay, number of nuclei in a sample. So sample, it means it could be whatever you're using. It could be, let's say, it could be a uranium nucleus, it could be a calcium nucleus, potassium nucleus, whatever the sample is. Okay, to half. Okay. Good. And so look, count rate equals number of counts per second. So this one here, when you use the Geiger counter, you're going to be getting counts. So every time you hear beep, 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 so per second, that's how much, that's the count rate. That's what you're recording. Okay, that's one. And let's have a look. The other one is activity. So activity here, it is the number of unstable atoms in a source that decay per second. Right. So this one here is from the source. So let's take a look. Let's say I have this one here. Okay, this is the source. It will start to decay, and that will be my activity. Let's say I have, where's my red pen? I have this red pen here, and this is my Geiger counter, which is the detector. I put it here. Now, since the source is decaying, so the decay could go either way. Okay, if there's no particular way, it can go right, left, up, down, sideways. Now, my detector, so all of these is the activity. So how active is giving off. Okay? Good. My detector is placed here. My detector can only detect particles that are going towards it. Okay, so every time a particles goes through the detector, I'll be getting one count. Okay, so let's say 1 beep, so beep 1, beep 2, beep 3, beep 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 beep. Good. Okay, so this one's only getting the particles that are going towards it. All the others, the detector is not getting it. Okay, as you can see, that's why we use count rate to tell us that number of counts per second that is being detected. Activity is just how much active the source is, how much is actually given out by the source. Good. All right, let's show some graph. Okay, have a graph. You will always have time here. Okay, you're gonna have activity on the y-axis or count rate. Okay, we'll always start at the big number and then it curve down like this. Always curve. No straight line, always curve this way downwards. Let's say we start at 80. Now how much we're getting. Okay, so half-life, how long it takes to reach half. So half of 40, so let's say 0 and then 12. Okay, so half of 80, half of 800, 400, and then to find the time, so how long, so what is the half-life? how long it takes to reach half. So half of 8 is 4, so go across this, hit the curve, and go down. So this number here, whatever this value here, let's say it's 2. So therefore, the first half-life is 2. Could be 2 minutes, 2 hours, depending on the time scale. Let's say 2 minutes here. 2 minutes. Good. Now, what is the second half-life? Okay. So it takes 2 seconds for it to go down by half. Now let's say half of 40, half of 4 is 2. It's going to be here, 2. I go across, hit the curve, goes down. Okay. And then this would be 4. Okay. So therefore the second half-life, how long is the second half-life? So if this is 1, this is 2, again it's 2 minutes. Okay. Right. So in this typical question, what they're gonna give you, they either give you some numbers and then just plot them. Just plot them, and you should always get this curve here. That's how you know whether you're right or wrong. If you plot your numbers and you don't get the nice curve, you don't get your numbers, your curve, or you don't get something like this one, then you plot it the wrong way. Okay. And when you want to find the half-life, always goes half, because across it goes down. Across it goes down. Good. In terms of half-life, that's all you need to know pretty much. pretty much it. There's one equation though, if you want to find out, so I'm just going to give it to you. So the equation here is count rate after n, we don't know n half-life. Okay, from this graph here, I can easily find the first half-life, the second half-life, I can even find the third half-life. So half of 200 is 100. I can go there and find it. I can easily find it. I can find even the fourth half-life, which is 50, but eventually reach a point where it becomes too small for me to find it. Therefore, that's where the equation come in. Okay, after n half-life equal the initial count. So here, in the case, initial count would be the number you start with, 800, divided by 2 to the power n. And n would be the n half-life. So in this case, I'll ask you girls, so example, hey, find 100th half-life. Okay, sorry, not find 100th half-life. Find count rate 400 half-life. So all you have to do, use the equation. So initial count is 800 divided by 2 to the power 100 equal, now let's take a look at the calculator, what it gives us. So let's take a look. Okay, so here we got 800, go down 2, power is this one here, 100. Okay, that's how much it becomes. So it's going to be crazy. So just write it as it is, yeah? 6.3 1 times 10 to the power minus 28. That's how much is left on this. So we started with 800. After 100th half-life, that's how much will be left. Very good. Okay, girls. Again, there's nothing complicated for half-life. You get the data, you plot it, get this curve. If you don't get this curve, then you use the wrong axis. Again, find the half-life, go half, find the time. Okay? And then always remember this equation in case they ask you for loads of half-life. Okay? It's done. Done. Again, I'm going slowly, girls, for you to, so that it makes sense. Okay. We are finally almost done. Number 7. Medicine. A piece of paper, medicine. There we go. A medicine. Or medical uses. Now, let's take a look. First of all, 2 keywords you need to understand. First of all is contamination. Okay. Contamination is when, let's say you have a source, a radioactive source, and you take it inside your body by either injection or eating it or drinking it. That's how you get contaminated, when the source is placed inside your body. So we're going to say when radioactive source, or could be a substance, is inside our body via, could be injection or eating, drinking. Yeah. Okay, so that's when you have to take it inside. The other one is what we called irradiation. This one is when you do X-ray, for example. You don't take anything, it's just when the wave hits you. Okay, so in this case, let me find a nice way to define it for you. Okay, right. Irradiation is when, okay, irradiation is when you are exposed to radiation as a wave. Okay, so for example, when you go for an X-ray, the X-ray, you get exposed to the X-ray as a wave. You don't take anything in your body. The doctor's don't give you anything to drink. You just sit there and just scan you. Uses radiation. It just passes through you. Good. Okay. Yep. That's it. Now, what are we talking about? Okay. Two things we need to know. Question gonna say is yeah. So why do we pick? So why? Let me just write it down. Why a particular isotope is used, or they're going to say why a short half-life, short life, it should be half-life, with the half-life isotope is used. Okay, these are the two questions they're going to give you. They can give you it as a scenario. They can say, well, the patient drank this much, and then why did he drink this one that has a half-life, short half-life compared to something else? The answer in this case doesn't matter what the question is. You need to talk about here. Now let's take a look. You're going to say, always this is the answer. The half-life, okay, is short enough brain freeze, short enough so no damage is done to cells. Okay, so you want it to be inside your body short enough so that it doesn't cause any damage. That's the first reason. Always the first reason. The second reason, so the half-life could be 8 days, 66 hours, 6 hours. Okay, but the half-life, okay, is long enough, okay, long enough for the test, okay, to be done. Good. Okay, and then the substance is going to will be out on your body by its half-life. Okay, these are the main two reasons. Okay, so if you go to the doctor and you need to do some scans, for example, you're suffering from there's something wrong with your bones, so then they will inject you with a radioactive substance, in this case contamination, that substance will go through your bones, and then they're going to scan you. And that substance, that substance could have a half-life of 66 hours. And then you can get the question, why do we pick that? One, it is short enough so that it doesn't cause any damage to your cells. Okay, so after 66 hours, it will drop by half, so only half will be left inside your body, and then after another 66 hours, it will be gone. Okay, so you're still safe. And then 66 hours is plenty of time to get the test done, okay, get the results, and still if you need to do another test, you can just go and do another test. Good. Right? Excellent. Here we go. All right. Also, if you guys remember, this should be fine. Should be fine. Okay. All right. So it depends on the half-life. Okay. And it depends on the type of radiation that is giving out. Now, when you go to the doctor, they will always say if they want to give you something to drink, which is radioactive, they will always give you either a substance that decays via beta decay or gamma. Okay. All right. The reason why. Okay. So reason why alpha source is bad inside our body, okay, it's because it has, if you guys remember, where is it? It's because of this ionizing power is very high. So high ionizing power, dangerous to cell, okay, dangerous to cell, can cause mutation within tumor. That's why we do not use sources that emit alpha particles. Excellent. Oh, here we go, girls. Almost done. Fission. 8. Fission. Fission. Un jour je serai le meilleur dresseur. Je me battrai sans répit. Je ferai tout pour être vainqueur et gagner les défis. Je parcourrai la terre entière, raquant avec espoir. Voilà, let's take a look. What is fission? So nuclear fission is a process by which a nucleus is split and release energy. Now let's have a look. So we start with. So first of all, what happens is we have a neutron. Okay, neutron is fired at an unstable nucleus. Okay, so if I want to draw it, I'm going to draw it like this one. This fired at all right. Second is a neutron is absorbed. Okay, so what's going to look like? It's going to look like, it's going to look like this. Okay, so just for the sake, I'm just going to draw everything the same. It's just like the dot will show that this one is indeed absorbed. And what happened is this one here is more unstable. Okay. It was already unstable. Now that it has absorbed the neutron, it becomes more unstable. And then it will splits into two smaller nuclei. Okay, so we have, so it goes into, let me just redraw it again. Okay, splits into two small one. One, two, plus two small nucleus, and then what we have is we have 1, 2, 3 neutron plus energy. Okay, so we have here we have the two small nuclei, the 3 neutron, and then energy. Okay. Okay. Releasing energy and 3 neutrons. Here we go. That is nuclear fission. First of all, neutrons fired at an unstable nucleus. This unstable nucleus absorbed the neutron, which make it more unstable, and then it split into two small nuclei, releasing energy and 3 neutrons. This is pretty much it. Okay. Good. Let's take a look. Now, we can use this in the reactor. We can use this in the nuclear reactor. Let's take a look how can we use this in the nuclear reactor. The second part we'll look at is something we called chain reaction. Okay. So to start fission, we need 1 neutron. Now, what happened is scientists thought that since we are getting neutrons from fission already, we can take these guys, use it to fuse, to split other unstable nucleus. That's the chain reaction. So if you guys remember, so I'm going to show you the books. Okay, if you guys remember, that's the one we were talking about. So neutron fired at unstable nucleus. Okay, it absorbs it, energy is released, splits, and then we release 3 more neutrons. These neutrons will go and hit other uranium and then split. So split, releasing energy, and then these guys here, 3 neutrons will go again, hit other uranium, releasing energy, splitting them, blah blah blah. Okay, so the chain reaction, what will happen is the initial reaction, okay, will cause the next to occur. Okay, so 1, boom boom, get this one, we take it, and then we start again. Energy is released, energy release, energy release. Okay, good. Now let's take a look at the reactor, because you need to know the 3 main part. Okay, we have moderator, we have control rod, we have fuel rod. Okay, fuel rod, that's where the fuel is, mostly uranium. Control rod, okay, what does the control rod do, girls? The control rods, when you lower it, when lowered, so it's like we have the container, okay, we have the fuel rod, okay, and then the control rods are there, so you can lower them in. Okay, so control, you lower them in. What it does is, when lowered, it will absorb extra neutron. Okay, so when these guys going out, any extra, it will absorb it. So if we absorbs it, okay, then there are less neutron to start the reaction again. So absorb neutron to slow down fission. Because now, once you absorb extra neutrons, there will be less of this. Less neutron hitting, less fission. Moderator is there to moderate, and it's normally filled. It filled the reactor. It's normally water or heavy water. So what it does, it slows down fast neutron to hit fuel rods. Yeah, pretty much. Moderator slows everything down so that the neutron can hit the nucleus and then fission can happen. We get energy. Good? Yeah. Okay, pretty much. Excellent, girls. Excellent. Let's have a look. What else do we need? Okay. Let's talk about the pros, cons. So cons is these could be radioactive. So what we end up with radioactive waste. Okay, and what can we do with this waste? That is very, very dangerous. That's a question. It is very dangerous. Very dangerous.